Okay, section 3.7, the chain rule. So there's two different ways to write out the chain rule, but we think of it as taking the derivative of a composition of functions. So suppose we have y equals f of g of x, then one way that we can write this out is to let u equal g of x, the inner function, and so therefore the derivative of y with respect to x is equal to dy du times du dx. The other notation for this is just keeping the f of g of x and writing the derivative as f prime of g of x times g prime of x. So the idea of the chain rule is that we're taking the derivative of the outer function and multiplying it by the derivative of the inner function. So let's look at an example of this. So the first example that I wanted to show you involved calculating the derivative of y equals sine of the sine of e of x. Okay? Oh, e to the x, sorry. So we have a composition, we actually have a triple composition here. So let's see how we can apply the chain rule. So I'm going to write out dy dx. dy dx is equal to the derivative of the outer function. Now here the outermost function is considered this first sine that I'm underlining. So the derivative of sine is cosine. And then we keep the inner function the same. So we have the cosine of the sine of e to the x. And then we multiply that by the derivative of the inner function, which is sine of e to the x. So the derivative of sine of e to the x actually involves another application of the chain rule. So we treat again sine, this sine here, as the outer function. So the derivative of sine is cosine of e to the x. And then, lastly, we multiply by the very innermost function, e to the x, its derivative. And its derivative is just itself, e to the x. And so our derivative is the cosine of the sine of e to the x times the cosine of e to the x times e to the x. So that's the first example. Next example. Okay, now suppose we want to calculate the derivative of y equals sine squared of e to the 3x plus 1. So again, we have three functions that are a composition of each other. Our outermost function, sometimes the hardest thing to identify is which is the outermost function, it's actually the square function. We have sine squared of a term. So if I were to rewrite this, it might be easier to see. I could rewrite this as sine of e to the 3x plus 1, the whole quantity squared. And then maybe it's a little easier to see what we're going to do. We're going to use the power rule and bring the 2 down front. That'll be our derivative of the outermost function. Then we'll work our way inward towards the sine, take the derivative of the sine, and then lastly we'll be multiplying by the very inner function, which is this e to the 3x plus 1 term. Okay, so let's take this derivative. We have dy dx is equal to the derivative of the outer function, which gives us 2 times the quantity sine of e to the 3x plus 1. And now we multiply by the derivative of the inner function here, which is sine of e to the 3x plus 1, which in and of itself, again, has an outer function. So the derivative of this outer function is cosine, and we rewrite the inner function and then multiply by the derivative of e to the 3x plus 1, the innermost function. And that gives us e to the 3x plus 1 times 3. Okay? So let's walk through that again. Okay, we had sine squared of e to the 3x plus 1. We took the derivative of the very outer function, 2 times sine of e to the 3x plus 1. Then we took the derivative of sine of e to the 3x plus 1 and got cosine of e to the 3x plus 1 times e to the 3x plus 1 times 3, where the e to the 3x plus 1 times 3 is the derivative of e to the 3x plus 1. Okay. Last example. Okay, so now we have y equal to the square root of x plus the square root of x plus the square root of x. So this one is a nested square root type function. I'd say the trickiest part of some of these chain rules is just keeping track of how far you need to go and where you're at. So one thing that I find helpful with rational functions is rewriting the radical as a rational function. So let's rewrite the radicals as rational exponents. So we have y equal to x plus x to the 1/2, and then this whole x plus x to the 1/2 is raised to the half power. And we close the parentheses, and then this whole thing, x plus the quantity x plus x to the half is raised to the 1/2 power. I find it's easier to calculate derivatives when you're using a rational exponent, but it is a matter of personal preference. Okay, so our outermost function here, I'm going to highlight it in red, is this 1/2 power exponent. Okay? So we'll handle that first. So we use the power rule. So we have y prime is equal to 1/2 times this whole inner function, which we just rewrite. Okay. And now by bringing the 1/2 down front, we decrease the power 1/2 by 1, so we have the negative 1/2 power. And now we multiply by the derivative of the inner function. Okay. So multiplying by the derivative of the inner function, well, first we run across this x, the derivative of x is 1, plus, now again we have a composition of functions. We've got x plus x to the 1/2, all raised to the 1/2 power. So we repeat the process here. The outer function of this guy is again a 1/2 power. So we again apply the chain rule, bring the 1/2 down, and we've got x plus x to the 1/2, all to the negative 1/2 power, times the derivative of this interior function, which I'm underlining in yellow, which is 1 plus the derivative of x to the 1/2, which is 1 over x to the 1/2. Okay, and I got kind of cramped there, so let me rewrite this whole expression. So we've got 1/2 times x plus the quantity x plus x to the 1/2 to the 1/2. All of that raised to the negative 1/2. And then we're multiplying by the derivative of the inner function, which gives us 1 plus 1/2 of x plus x to the 1/2 to the negative 1/2, times the derivative of that interior function, which is 1 plus 1 over x to the 1/2. And actually I forgot a 2 here. It'd be 1 over 2 times x to the 1/2. Okay. So what we have is a chain rule within a chain rule, essentially. Okay, so that's all for this lesson.